Good evening, sir, everyone. For today, we are going to the talk Dr. C.V. Kannan from the Tata Power Systems from Tirunelveli. Sir already completed PhD. Maybe let us introduce sir. I would like to request the Kajal Agrawal introduce sir.
Good evening, everyone. It is my great pleasure to introduce an extraordinary leader in the field of photovoltaics and material science, Dr. C.V. Kannan, who brings with him over 22 years of experience, including nearly 18 years in the solar PV industry. Dr. Kannan holds a PhD in material science from the Crystal Rose Center at Anna University, Chennai, completed in 2002. He also completed a prestigious 4-year postdoctoral fellowship at the National Institute for Material Science (NIMS) in Japan, renowned for its excellence in material science and academic industry collaborations. Since 2007, Dr. Kannan has been associated with top industry players like GT Advanced Technologies, Mosbaer, PV India, and Adani Solar, where he played a pivotal role in developing gigawatt scale crystalline silicon ingot wafer, advanced cell, and module technologies. Currently, he is leading the engineering, technology, and quality functions at TP Solar Limited, a Tata Power Renewable Energy Limited subsidiary, spearheading a 4.0 gigawatt manufacturing faculty for advanced crystalline silicon PV cells and modules. Dr. Kannan's exceptional contributions have earned him several accolades, including the Young Scientist Award by the International Organization of Crystal Growth and the Young Research Award at IUMRS Bangalore and the Special Researcher Award from NIMS Japan. With nearly 35 technical publications in peer-reviewed journals, his work is widely recognized in the global scientific community. Dr. Kannan is a visionary combining academic excellence with industrial innovation to propel India's renewable energy sector to new heights. Please join me in welcoming Dr. C.B. Kannan. Thank you, sir.
So welcome, sir. Welcome to the FFB talk.
Thank you, Dr. Thankavil, and thanks for a nice introduction. And first of all, very good, warm and very good evening to everyone. And yeah, I will share my presentation.
So I will include sound. You can use as while sharing. You can include sound.
Are you able to see my presentation?
Yes, sir.
Yes, sir.
Okay. So anyway, yeah, my name is Kannan. So I'm heading the, as I said, I have 18 to 20 years of PV experience, and right now I'm in Tata Power Group. Recently, they set up one of the India's largest, cell plus module manufacturing facility in southern part of India, and I'm heading the engineering and the quality function of this one. So I'm really happy to share some of the learnings which I have, gathered last few years in overseas and India about the PV, photovoltaics. I'm sure I think you like this presentation because last 2 days you have been getting a lot of more technical insights, about the different processes. And here I'm going to talk about a little bit different for initial few slides about the market, because which is a hot topic right now, about the renewable energy. Everybody's talking about renewable energy. Why? What is the importance of the renewable energy? Then I will get into the subject of crystal growth, because today topic is the wafer processing, but tomorrow is crystal growth, defect control and methods. So I requested Dr. Thankavil to switch over because I want to start with the crystal growth first, then wafer starts, followed with the crystal growth. So today we'll talk about some of the market, what is happening in the PV industry, photovoltaic industry, and where India stands, and what are the different crystal growth technologies for the PV point of view. Of course, a semiconductor also using different type of wafers, but I will touch only the PV part. Then tomorrow we will talk about how to process the wafer. Once you grow the crystals, how to convert the crystals into the wafer for the different applications, right? So the topic today topic will be, I'll cover up the TP Solar. What are the different products we are offering, and why the renewable energy getting towards getting more attention recent past, and where is the global PV market, where India stands in the photovoltaic market, because everywhere people are talking about renewable energy and particularly solar photovoltaics. So I would like to bring some insights about where the global PV market stands, where India stands, so that you will also get some feel, okay, what to do to reach the target of 1.5 degrees C. Then we will get into the manufacturing process of solar PV value chain, and particularly ingot and wafer. Then what are the different advancements are happening in the ingot side and wafering side, right? So the bottom one, maybe I will show my slide. Sorry. Points option. Yeah, if you look at the bottom side, when you talk about solar value chain, normally most of us, we saw in many panels installed either in the field or maybe in the roof of the house. And before the panel installation, there are so many processes involved. So when you call solar PV value chain, it starts from all the way from quartz, a material. That's a quartz, that is a SiO2. From quartz, it will convert it into low pure metallurgical grade silicon. It's a low pure silicon. Then the low pure silicon will be converted into very high pure silicon, and through different chemical processes. Then it will be converted into the crystal shape, either cylindrical form or square shape. That depends on the what kind of growth methods you are using. Then these crystals will be converted into wafer, and with the different sizes, different thickness, and then these wafers, or you can say substrates, will be converted into the semiconductor device, like a PV photovoltaic PV cells. Then the PV cells are stitched together to convert into the photovoltaic module, or you can say panels. Then these panels will be installed into the field. So the entire stream we call is a PV value chain. It starts all the way from quartz to the PV model, which you all are seeing in the field or in the roof of your system. So most of, if you see here, TP Solar, I'm part of Tata Power Solar. So we are present in the extreme, downstream of the value chain, where we make the solar PV, we get the wafer from outside, convert into solar PV cells, convert into module, assembling the cells into module, then send to the customer. And but if you look at the China, they're almost all the way, entire value chain is available in China. Almost 90 to 95% of the value chain starts from metallurgical grade silicon to the PV modules. So entire value chain lies in China. That's the biggest difference between India and this one. So before I get into that subject, core technical subject, these are some of the terms I used in the presentation. I want to clarify before you should not get confused. So most of the places we used watt peak, WP. That means how much power the panel can generate, how much power the small single cell can generate. And whenever we talk about capacity, plant capacity means normally we talk about in megawatt scale or gigawatt scale. So 1 megawatt means 1000 kilowatt, and 1 gigawatt means 1000 megawatt. Then also we talk about solar irradiance and kWh, and another PV system or PV tracker. These are the small, acronyms, normally the digits we used in the presentation. So before I get into the subject, I want to say a few things about TP Solar associated right now. And Tata Power Solar, basically it's almost 25 to 30 years old company, one of the oldest company in India, where the PV, cell and model manufacturing started in the way in 1991, along with the BP, Bharat Petroleum, a joint venture. And since then, they have been in the solar PV, photovoltaics manufacturing in terms of cell and module. And the oldest factory we have in Bangalore. And recently, that capacity was only 600 megawatt. And recently, as a part of expansion plan, so the management set up India's largest single location, 4.3 gigawatt of cell plus PV cell and module manufacturing facility in southern part of India, close to Tirunelveli, close to Kanyakumari, just 100 kilometers north of Kanyakumari. And also recently, we are also planning to set up another 2 gigawatt of module manufacture. 2 gigawatt means 2000 megawatt of module. Whenever I say capacity means annual capacity, the plant can generate 2000 megawatt of equivalent panels produced in that particular facility per annum. So another 2 gigawatt or 2000 megawatt of facility planning to set up in Jodhpur in Rajasthan, where the market, most of the entire end use market lies in the Gujarat and Rajasthan. So management decided to set up the facility over there. So the top one is the Bangalore facility, is the oldest 30 years old facility. And the bottom one is the recently it's getting built just a few months before we built this facility. It's almost 300 acres. It's almost covers 300 acres of land in the highway. And yeah, so this is the one of the first plant, I would say, probably say that one of the first solar PV manufacturing plant in gigawatt scale with 100% automatic guided vehicle. Normally, most of the solar plants, they have a manual operation. This is the first plant with the entire 4.3 gigawatt scale, complete automated. And another important thing is with 80% women workforce, most of the employees we are almost 3,000, 2,500 to 3,000 employees are there. Out of the 3,000, almost 80% is women workforce, all from the nearby districts. So this is one of this indicates that how Tata is empowering the local area, the women empowerment, and also the a job for the local community, right? So these are the different products market we are offering. And maybe 5-6 years before, the solar panel, each panel can produce per hour 300 watt, something like that. But because of a lot of technology developments and product design change, right now the 330 or 360 become close to 650 to 700 watt. Similar kind of module size, where the power almost doubled. That indicates that power density has doubled. So automatically, small area where it was generated certain amount of power, the same area, same size of panel now can generate double the power of what it has generated few years before. So a lot of technology development happens. So if you see half cut 144 cell, I think I will discuss later. And different number of cells you add it, automatically power generation also will go up. And recently, all these, when you talk about half cut, means normally the cell will be square shape. And recently, instead of square shape paper, the industry also moving towards a rectangular shape, so that you can pack more number of wafers and more amount of silicon area cover up in a small area, so they can minimize the empty spaces. So you can accommodate by using rectangular shape wafer, you can increase more packing, you can increase the packing density, so that automatically power generation will be higher. So a lot of developments are happening. The wafer area will go one by one. So anyway, what is why the people are giving more importance to the renewable energy? Everyone talking about renewable energy, net zero, carbon neutrality. So they're talking about so many different terms. And ultimate goal is to maintain the global average temperature to maintain at 1.5 degree. Right now, the global average temperature has increased 1.2 degree from the pre-industrial area. When you talk about pre-industrial area, it's 1900, almost 100 years before. What was the temperature? Now the global average temperature has increased to 1.2. And if the situation, the scenario continues like this, probably the temperature may go even 2.5 to 3 degree, then nobody can survive the world. Even 1.2 degree in average temperature increase, we are seeing so many natural disaster and calamities, right? So the entire the government or different countries, they're trying to find out how to control the temperature at least 1.5, not to increase beyond 1.5. That's what you can see everywhere, path 1.5 degrees C. And but unfortunately, what is happening here, this curve indicates that if you want to reach 1.5, then our amount of carbon global greenhouse gas emission should be this level. But where we are right now, still we are here. And if you continue like the current scenario, the after 2100, after maybe 80 years or 75 years, the temperature you cannot bring down to 1.5. The temperature will be 2.5 and to close to 3 degree. Then nobody can survive. So even if you're optimistic, like whatever the government, they are putting a lot of efforts how to minimize, they are setting a lot of targets. If everyone achieves the target, probably it will bring down to 2.1 degree. But reaching 1.5 degree, certainly a lot of efforts need to be done, and beyond whatever the commitments are given by different various countries, right? So right now it's a 2020 itself, 25 itself, there is a huge gap already generated. We have to supposed to produce to achieve 1.5 degree, the greenhouse gas reduction should happen like this, but we are almost double than what is supposed to be. So there are a lot of efforts, combined efforts is required to bring down the greenhouse gas emissions so that overall global average temperature to control at 1.5. So then only the next generation can survive. So this is what, to reach that carbon neutrality or, the net zero. So we are supposed 2030, the amount of greenhouse gas emissions should supposed to be minus 45% than what is supposed to be in 2010. But actually what is happening, so we are instead of minus 45, already we are plus 9% of, what our target. So that indicates that, we are not in align with what we have committed in the different meetings in the Paris Agreement, climatic agreement. Everybody talking, but still reality is not happening. So if we go like this, probably we cannot maintain the temperature to 1.5. It may go to even 2 degree or 2.5 degree. Then we may expect a lot of natural disasters in coming years. And this one, okay, this is the overall energy resource. Whatever the electricity we are using right now, what are the different sources used for generation of electricity right now? Currently the major electricity source, generation source, is a coal, almost 30 to 40% coming from the coal and natural gas or oil. All these are all fossil fuels. Only maybe 8 to 15% maximum, including nuclear, from the renewable energies. But going forward, maybe after 20 years or 30 years, we may expect the renewable energy share will go beyond 40%. That's what everybody predicting. But even if you go with 41%, 50%, or 70% of renewable energy, still the amount of greenhouse gas emission, we cannot bring down to that level where we can achieve a global average temperature less than 1.5 degree. So the right side graph is clearly indicates how much amount of greenhouse gas emission when we per unit of electricity generation by different sources. So for example, coal, if we generate electricity through coal-based electricity, for each unit which we are consuming at home, each unit of electricity through coal generates close to 0.8 to 0.9 kg, almost close to 1 kg of carbon dioxide we are releasing to the environment. And similarly, oil, natural gas. If you look at the photovoltaics, it's almost very, very low compared with the coal. So that indicates, if you use more electricity consumption generated through coal, that means we are releasing more amount of carbon dioxide to the environment. That's the reason in all the nations, they are focusing more on the renewable energy, where the photovoltaic, hydro, wind, and nuclear, where the amount of CO2 generation per unit of electricity generation is relatively very, very low. So by transition from coal, fossil fuels to renewable energy sources, we may cut down the amount of CO2 released to the environment. In that way, at least we can minimize the emission. And even by doing this, it's very difficult. That's what is predicted, that it's not that easy to bring down that level where you can control 1.5. At least they're trying to control 1.5, maximum 2 degree. So this definitely certainly needs a combined effort from everyone, how to bring down to maintain that global average temperature less than 1.5 or less than 2 degree maximum. So when you talk about value chain, these are renewable energy. When you talk about value chain, as I said, it starts from polysilicon, ingot, wafer, cell plus module, broadly 4 verticals. And if you see here, the polysilicon capacity, the global polysilicon capacity is almost 2000 right now. If we say 2023-24, so almost 1189 gigawatt equivalent polysilicon is available. But if you see this curve, the last top side 2 lines, so almost 90% of the production capacity is available in China. 90%. Or more than 95%. Almost entire polysilicon, which is the key raw material for any wafer manufacturing or a crystal ingot manufacturing to, for any photovoltaics or maybe any other semiconductor devices. So 95% of polysilicon is being produced in China. Same thing if you see the wafer capacity. See, India, mostly we have a solar cell and model manufacturing. We are importing wafer from China. So we do not have any own wafer manufacturing facility. So that wafer also 97% is being produced in China right now. It is expected maybe slight dip, but still more than even after 2030, still they will dominate 90% of the entire manufacturing capacity of key raw material, the upstream product like polysilicon and ingot wafer will be from China only. And this is once again the next downstream product, cell and module. Even though India has some capacity of solar cell manufacturing and module manufacturing, but still China dominates in these areas also. That indicates the entire value chain. More than 80 to 90% of the entire value chain is dominated by China. That clearly indicates that they are controlling the entire solar PV value chain. So unfortunately, none of the countries other than China having the entire value chain. India, of course, we have solar cell plus module, and we do not have the backward or upstream product like a polysilicon ingot. So recently, government is trying to push a lot of efforts to investment on the upstream product like a polysilicon ingot wafer, but that is also getting delayed because of various reasons, right? So recent, because of the overcapacity, China, they are controlling the entire polysilicon. Recently, there was a huge overcapacity that brought down the entire polysilicon price. This is the raw material. Once the polysilicon price has come down to $30 per kg to even now $6 per kg within a year, see the drop. So when the raw material prices come down, entire value chain, wafer prices come down, cell prices come down, module prices come down. One way it's good also. So overall the module price has come down so that many people can afford the installation of solar photovoltaics. The overall solar module price has come down, but still it's driven by the China. So one way it's good for the installation purpose. You can buy the module from China and you can install it. But the people, the industries, the manufacturers who set up the facility in India or rest of the world, they're not able to compete with this cost pressure. So including Indian manufacturers, they're struggling because they have an overcapacity and getting a lot of subsidies from the government, and they can manage, they can afford this kind of fall in the price. But when we are getting this much low price, Indian manufacturers, they're not able to meet because the volume, because they are having 90% volume, we have only 2% volume. So it becomes a volume gap. Whoever having more volume, they can control the cost. That's what happening in the industry. And okay, when you talk about India, you all know that India also set up ambitious target, and you all know that the carbon, net zero government has, our Prime Minister, Honorable Prime Minister announced the net zero for India will be achieved 2070. So to achieve net zero, he set up at least interim target of 2030. Right now, another 6 years from now, he set up a target of 500 gigawatt of generation capacity through renewable energy. Only through renewable energy, only 500 gigawatt he has to achieve before 2030. And as of now, almost six years left, but so far we have done only 200. Recently, last month only we crossed 200 gigawatt. Still 300 gigawatt to be installed in 6 years. That needs lot every year 50 to 60 gigawatt of installation has to happen. Right now in India, last 2 years it is happening only 10 or 20 gigawatt of installation. Even lot of push from the government, still it is happening only 15 to 20 gigawatt. So this has to be 3 times, then only we can achieve our at least 300 500 megawatt of target in 2030. But so far, India is one of the second or third biggest, market compared with China is the dominating in installation also. Then US and India becomes the third market where a lot of installation demand for solar PV photovoltaic installation is happening, but manufacturing still not up to the mark. Right. If you look at this graph, maybe I'm not sure whether you guys, you all know about these companies. This gives overall view of, of all in the cell capacity and module manufacturing capacity. And cell capacity, so many players are there, but still the blue color says that already existing capacity, if you see only 8 to 9 gigawatt capacity is only available against 700 gigawatt of cell manufacturing capacity in China, where we are talking about only 7 gigawatt, 1%. China is almost 97%, we are 1%. So how do we compete? So if you look at the module downside, right now we have 35 to 40 gigawatt of capacity, and it is expected maybe another 2 to 3 years it may go to 80 to 90 gigawatt capacity. But once again, it is 10% of what China is holding right now. So it's expected another as I said, government is pushing a lot of efforts to improve the local manufacturing capacity of both solar cell and module, and wafer also they are pushing, but still a lot of challenges to enter into that upstream or we can say downstream product of wafer and polysilicon, which is the capex intensive and also power intensive. India electricity price is one of the highest electricity price in India, but those upstream products needs very low electricity price, where China they are getting subsidized electricity. That's why they are able to produce at a lower cost. And okay, now we will get into the real area. Though the value chain starts from MG silicon, metallurgical grade silicon, polysilicon, ingot, wafer, cell, and module. And today and tomorrow we are going to talk about only ingot and wafer. What are the different technologies or growth methods available to grow a good ingot? Then what are the different slicing mechanisms, how to prepare a good wafer, and what is the importance of the wafer quality into the overall performance of the upstream, like a cell efficiency, how the wafer quality improves the overall cell conversion efficiency, and if the efficiency of the cell is good, then the module watt power also will be very good. Then when you install those module into the field, your generation also, you can generate more electricity. So we are talking about only today and tomorrow talk about only ingot and wafer. So when you talk about ingot, when you talk about wafer, there are 3 different type of wafers are available. One is monocrystalline wafer, another one is multi-crystalline wafer, and another one is amorphous silicon. So today we are going to talk about only crystalline. And if you look at overall PV industry, there are some thin film technologies available, and panel can be produced through thin film, and panel can be produced through crystalline silicon wafer. So when you talk about crystalline silicon, there are 2 type of wafers. One is polycrystalline, or you can say multi-crystalline wafer, this one, and another one is monocrystalline wafer. You all know that what is the difference between amorphous and multicrystalline and polycrystalline and single crystalline. So polycrystalline is nothing but combination of monocrystal, small monocrystalline. Whereas the monocrystal, where the performance or parameters of the characteristics of the entire wafer is same and single direction, whereas multiple polycrystalline, multicrystalline, where the wafer orientations are different, so the performance parameter, the characterization of the individual crystals are different. So the overall performance of multicrystalline is relatively downside than the monocrystalline. So until a few years before, the multicrystalline was so dominant in the market, and since because of the multicrystalline, a lot of grain boundaries between the crystallites, so there was some limitation in the efficiency. And since the technology is going up, they need very high quality wafer to and drive the efficiency further up. And multicrystalline has some limitation because of grains or grain boundaries. And whereas monocrystalline is a single crystalline, so that there is a potential to improve the efficiency further. So because of that, now the industry is moving towards monocrystalline wafer based technology, right? And of course, the thin film amorphous based thin film technology is also available in the market, but still the the overall performance of efficiency, conversion efficiency, model power is not competitive to crystalline based technology. So 95%, 96% overall PV market lies in the crystalline silicon case, and either polycrystalline or multi or monocrystalline, mainly dominated by the monocrystalline technology because of the efficiency increase. So these are the different different crystal growth techniques available in the market. When you talk about crystalline silicon, there are two major division. One is multicrystalline, where, as I said, the crystallines are not oriented properly, so that multiple small crystals in a single area, so that performance is relatively poor. Another major portion is a monocrystalline silicon. And even if you monocrystalline silicon, there are two major one. There is a float zone technique. Another one is Jaworski, which is the major dominant technique available in the market. And if you look at the multicrystalline, so there are another two more techniques like a ribbon growth and casting, DSS, directional solidification system. So these are the four different methods normally available for this one to grow the crystalline silicon wafer, but mainly dominant by the Jaworski, because you cannot grow monocrystalline through this technology. And high purity monocrystalline technology, you can grow either Jaworski technique or through float zone technique, right? Mostly the float zone technique is more pure. I think the previous presentation also, one of the audience, they raised the question which technique can produce very high pure crystalline silicon substrate. So here is the answer. The float zone will produce very high pure quality, and mostly they used for semiconductor application, where the IC chips and fab and all those things, where you need a very high quality and less amount of oxygen, all the other impurities. So the float zone technique, you can grow very good purity because you are not using any kind of the crucible and any material where you can pour the polysilicon raw materials. Here there is no crucible, so it's a non-contact. Automatically whatever you have a raw material, that will be converted into crystal in a very pure form. There is no contamination from other areas. And whereas in the CC Jaworski process, we will go in detail into what is Jaworski process, what are the different steps in the Jaworski process. I will come to the next slides. Jaworski process is the major dominant process. It's been in the industry for more than 70-80 years. And even Jaworski also, there are two things. One is a standard process, then upcoming process. Means standard process means normally, when you load the material, you melt it and start pulling the crystal. Maybe earlier standard means only one time you fill it, one crystal you can get it. Now, because of technology advancements and there is a cost reduction activities, so you can grow one crucible. Crucible means one small container, quartz based container, where you can pour the material, heat the material to 1400 500 degree, right? And instead of one crucible, one crystal, now only one crucible where you can grow multiple crystals. so that they maintain the melt level, and continuously you can grow the crystal, then pour the material parallelly and melt it, so that you can maintain the melt flow, solid liquid interface level, where you can grow multiple crystals. That way you can minimize the downtime, not minimum downtime. You can produce many number of crystal in small sort of period of time. In that way, your productivity will improve automatically. When productivity goes up, automatically cost will come down, and quality also you can maintain because you are maintaining the melt level, right? So these are the different 4 techniques, and the next slide shows the comparison, overall comparison between what is positive, what's the pros and cons of each and every technique. As I said, directional DSS growth, you can, because it's a you can multi-crystalline, you can grow only multi-crystalline silicon wafer in this technique, where you can grow the different size because it's a square shape, and whatever the size you want, you can cut it. So any wafer size you can produce, using this multi-crystalline wafer, and you can produce square wafer, rectangular wafer, whatever the shape you want, you can cut it. And overall capital equipment cost is very low, and process cost, overall the manufacturing cost will be very low. That's the reason maybe a few years before, industry was focusing more on the multi-crystalline growth, because the low cost you can produce high numbers of wafers. But disadvantage, cons, pros, pros are these are things, and disadvantages, because it has a multi-crystalline, multi-grinds, overall minority carrier lifetime. That means when the sunlight falls on that, electron hole pair will be generated, and lifetime of those carriers, minority carriers, is relatively lesser here, because you have a multiple grain boundaries. So it will be trapped in the boundaries, so that minority carrier lifetime will be very small, so that you may not get the desired efficiency. And that's the reason conversion efficiency very low. And in contrast, if you see the CC growth, and it's a single crystalline, instead of multi-crystalline, you can grow a single crystalline, and since it's a single crystalline, you can grow the conversion efficiency is very high. But the problem is, you can grow only the cylindrical form, and you cannot increase the wafer size beyond, because your cylindrical, the crystal size is limited. You cannot grow just like that. You cannot increase the crystal diameter just like that. So wafer size is limited. Not only that, and when you grow single round crystal, and if you want to make a square wafer, you have to cut it down, so that a lot of yield loss will be here. So overall manufacturing cost will be relatively higher, and also cost of the equipment is very high, and you can grow only round crystal, and you can grow only the quasi square. You cannot make fully square wafer, or different sizes also. And also in this case, the oxygen concentration will be very high, whereas in the multi-crystal DSS growth, oxygen concentration is very low. So there are some advantages in terms of efficiency, but there are some disadvantages. But despite having so many disadvantages, now the market is moving towards monocrystalline, CC Zaworalski growth, because of its high efficiency, single crystalline nature. So the upcoming technology, the future technology also, they need very high pure substrate. So that can be, grown only through CC growth, right? That's the reason it's another, as I said, float zone technique, where there is no crucible, and whereas silicon here, crucibles are used. So all the molten polysilicon is in contact with the crucible. Crucibles are not very high pure, whereas the raw material is very high pure. So there is a contamination from crucible to the melt, so that contamination will go into the crystal also. Whereas in the float zone, there is no crucible. So the rod is melting and converted into the crystal. That is the reason the purity of float zone method is very, very high compared with other techniques. Another one is EFG, but this is not in the market right now. These are the 4 major broad level crystal growth technology, and where normally these float zone mostly they used for IC and semiconductor. And these 2 techniques mostly they use for solar PV applications. So in addition to that, there are some different new methods, wafer phase. Tangavel, please, along, give me along in case any time, restriction, right? Because I don't want to exceed the time. Dr. Tangavel?
Sir, time available, sir. You can do it, no problem.
Okay. Whenever you want to stop
Yes,
it,
sir.
it is
Available, sir.
Okay. So in addition to the crystalline silicon, there are some methods where you can use the gas phase. Instead of using polysilicon, you melt it and grow in a square shape or cylindrical shape, then cut it. So many different processes. So there are industries also try to grow the wafer shape through gases. Directly you can deposit on some substrate, then you take out that top, cleave that in top deposited surface, so that you can use that as a wafer. But unfortunately, that wafer thickness will be very, very through gaseous phase. You cannot grow even micron level. It will be nanometer level, or maybe 1 micron, sorry, 10 micron, 20 micron, 30 micron, that level. You cannot grow 200, 300 micron. Whereas in the previous, all these cases, you can grow even 300 micron, 400 micron, 200, whatever the thickness you want. You can design what thickness you want, what shape you want. So a lot of flexibility there. Whereas here, you have limited with the wafer's thickness, but the purity, because you are converting gas directly into the wafer format deposition. So the purity of the wafer, even the thickness is very small, the purity will be very, very extreme. But since the thickness is very small, not that easy to handle to the next upstream process. When you convert into the solar cell manufacturing, and handling such a very thin wafer is not that easy. So there are some challenges, but still industry is working on that. And another technique, directly, because instead of polysilicon pouring into crucible, melting, converting into crystal, so there is a one technique, from US. One company was trying to establish a new technique called direct wafer. So without any crystal, just pour the polysilicon, then melt it, and just spread on the some substrate, take out the wafer. You can maintain the thickness and all those things. But once again, you can grow whatever the shape you want, whatever the thickness you want. But unfortunately, you cannot grow very high pure monocrystalline here. You can grow once again in the multicrystalline format. So as I said, multicrystalline, there is a limitation in terms of efficiency. You cannot go beyond certain size, right? Quality also, you cannot increase the quality. So these are the different techniques available in the crystal growth areas. And but all are wafer, crystalline wafer, through CC Zogorowski, just using the polysilicon, high pure polysilicon material, then convert into a wafer with a different size and thickness. And here using the gaseous, different gases, silane, trichlorosilane, silane gas, you dissociate silane into silicon, into H2, then deposit that silicon into a different substrate, and after certain time you can take out that thin substrate and use for further processes. And another technique is a 1366, a company where instead of converting into square shape but cylindrical, directly melt it, directly pour into the substrate, then take out the wafer. But unfortunately, it's a multicrystalline format. You cannot use it for high efficiency technology. So a lot of every technology has its own pros and cons, but these are the broad level of different type of technologies available in the market. So when you talk about DSS, we will go. We're not going to discuss all the 4 technology. We talk about only 2. One is direction solidification, and another one is the Zogorowski process, right? So here we are talking about directional solidification process, how the process works. So directional solidification means there is no pulling process. So there is a crucible, and the high purity polysilicon. This is the high purity polysilicon. The purity of silicon will be 9N, 10N. When I talk about N means 99N means 99.9999, that much of purity. Ultimately, we need 100% purity, but you cannot achieve 100%. So the previous low quality silicon will be 99.5% purity. So the 99.5% purity will be converted into 9N or 10N purity of high purity polysilicon, and through chemical processes. and then this will be loaded into the crucible, and this crucible is a silica crucible. Then there is a susceptor to protect the crucible to deform and damage. Then it will be loaded into the furnace, and then the furnace will get heated. The polysilicon material which is inside the crucible, it gets melted, and then after that there is a controlled cooling from the bottom. So after melting, there is a cooling from the bottom. So the bottom side there is a cooling mechanism. So the crystallization starts from bottom, then the interface will move from bottom to top. So the solid liquid interface move from bottom, then it slowly move, because we are extracting the heat from through the bottom through some cooling plate, so that because of the temperature gradient, so bottom side will become crystalline and top side will be molten. That's solid liquid interface will move from bottom to top. The automatically the crystalline, the crystal starts going from top to bottom slowly, something like that, right? But since it's a sudden cooling from the bottom, so you may not expect the pure crystalline. It will be a multi-crystalline format, because you are quenching, because you are molten the complete silicon, then suddenly you start cooling. So you may not expect a good crystalline nature on the bottom. There will be a multi-crystalline nature will be generated on the bottom of the crucible. Then the multi-crystalline crystal will start growing like this, so that there will be a columnar growth all the way from bottom to top. And in this case, you can change the you can load more amount of crystal, because based on the crucible size, you can mix more amount of raw material. Also, you can grow big crystal, then you can cut according to the wafer size, whatever the wafer size you want, right? But one of the disadvantages is a multi-crystalline growth, and the crucible walls are highly contaminated. So whatever the silicon which is in contact with the crucible, so the close to that area, the quality of the silicon material is very poor, because a lot of contamination coming from the crucible wall through the solid state diffusion. So the contamination is very high. So only the center portion of this complete ingot will be better, and this area, the edges close to the wall, the contamination is very poor. Than if you convert this area into wafer and use per cell, the minority carrier lifetime will be very poor. The conversion efficiency also will be less. So this is the process. After you convert convert into solid piece, then you take out the crucible. Then the crucible will be like this. It's a square shape with the 30 centimeter or 40 centimeter height, with the 1.1 meter or 1.5 meter width. Then you just take out the edges, because as I said, the crucible in contact with this this one, so a lot of contamination. You have to remove those low quality wafer area, slice it, then you will get very good area here. Then you slice this according to the wafer size. Then you have to cut it like a cake according to the wafer size, whatever the wafer size you want. If you want 182, 156, whatever the square shape wafer, 156 or 182 or 210, whatever the size you want, you convert. You can use this as a ingot into different shape, convert like this. Then you will get a simple brick, right? Then you can convert this brick into wafer, whatever the thickness you want. You can slice it, so that you will get the wafer of desired size and this one. But unfortunately, this is the multi-crystalline wafer. So the manufacturing cost, overall manufacturing cost, will be relatively lesser, but the quality of wafer relatively poor. So maybe 2 to 3 years or 4 years before, this was the dominant growth methods in the industry. But now the industry demands very high quality wafer. So through this technique, you cannot grow beyond a certain quality. So that's why this method is almost getting phasing out of the market. So if we see this one, is another way of schematically looking at. So you have to load the polysilicon into the crucible. Then after melting, just extract the heat from the bottom. So automatically the molten bottom side will become solid. Then you keep on extracting the heat from the bottom side. So this crystalline interface will move from bottom to top. So this crystalline columnar growth will start. So finally you will get a crystal like this. Then maybe some small poor quality of material will be underlying of this one. So we have to cut all the sizes, then convert into bricks. Then you have to slice the brick according to the wafer. You will be getting like this. So this is the overall furnace design, and where the crucible, this is the off semi portion of inner side of the crucible, where the crucible will be lying here and polysilicon will be loaded here. Then initially this will be closed, and there is a heater here. The heater will heat the complete polysilicon material. Once it reaches a certain temperature, then there is a cooling chamber. This is the chamber where the cooling water, 18 degree cooled chill water is flowing with the high flow, high pressure. It is flowing on the chamber, and during the melting process, the chamber is completely isolated through this heat insulated mechanism. This is completely packed. No heat will pass through. After melting, complete melting, when you want to start the process, when you ensure, okay, everything melting, now I want to start the crystal growth process. So they will just open this, side insulated wall, this one, side insulated graphite wall. Then automatically this area, the crucible bottom is exposed to the cooled chamber, water cooled chamber. Then the heat will start dissipating through this graphite plate. Then it's going to the this one. So automatically the bottom side temperature will be relatively lower than the top area. So crystallization will start. Then you have to you have to move this plate and ensure there is a controlled way of extracting the heat, so that the growth also, without any major disturbance, the growth also will continue very smoothly from bottom to top. So in that way you can maintain in the crystalline quality, and this is the way we are DSS works. And now what is happening this way right now, it's a multi-crystalline. So now another improvement happening in the multi-crystalline is, instead of only crucible, they put some monocrystalline seed at the bottom, monocrystalline a brick at the bottom of the crucible. Then if you start it, so whatever the crystal initiated from the monocrystalline bottom seed, the quality of the wafer will be relatively better than multicrystalline. It will be in between pure monocrystalline grown by Jaworski process and multicrystalline grown by DSS. That's a mono like multi. There is another technique, by using the same equipment, you can put some seeds at the bottom, so that try to grow a monocrystalline kind of nature. But that also, once again, it's a cost, is increasing. The quality is not up to the mark of pure monocrystalline. So by doing this mono like multi, also the quality of the wafer or purity of the wafer is not equal to conventional CZ process, Jaworski process, where you can grow very high quality monocrystalline wafer. That's why this technique, DSS technique, is getting phased out from the industry. Now almost 95%, or you can say 99% of the crystalline silicon wafer crystal manufacturing is happening only through the Jaworski process. This is the one of the important process in the PV. Not only PV, even semiconductors. When you talk about silicon or germanium, most of the semiconductor materials are being grown by Jaworski process. It was developed in the year of 1953, right? And almost 19 one Czech scientist, his name is Jaworski. He only invented this technology, Jaworski, right? So since then, it's being one of the key growth methods in the entire silicon, ingot growth mechanism, and applicable for both semiconductor and also PV applications. So if you look at the CC puller, looks like this schematic view, and this is the final crystal. The Jaworski puller will be like this, and this is the chamber where you keep the crucible and raw material inside. And there is a motor here. It will rotate this one. This is the where you can pull the crystal. So cylindrical crystal will be grown here. After grown the crystal, you take out this one and take the crystal out, then put the new material and all those things. This is the hot zone, right? This is the one schematic view. So if you see here, there is a paddle where the crucible will be placed, and inside the crucible you put the polysilicon, high pure polysilicon material. So during the growth process, the crystal will grow pull like this. Same time, the paddle also will rotate. The crucible also will rotate, and bottom paddle on the crystal. The crystal also will rotate, and crucible also will rotate opposite to each other. That way, you ensure that the melt is uniformly mixed, and you can get the very high pure crystalline. So this is the overall schematic view of a crystalline silicon. So this is the process. It starts from crucible, and we use the high purity polysilicon. As I said, a very high pure 9N, 10N purity polysilicon we should load into the crucible. And this crucible, when you talk about crucible, it's a quartz material, very fragile material, and this is the only material where less contamination, and it can withstand even 1400, 500, up to 1100 degree. It becomes softened, but still you protect with some acceptor so that the crucible will be intact. And then you fill the you melt it so that becomes melt, then stabilize the melt. Then here the previous DSSS, there was no seed used. So after complete melting, you started cooling from the bottom, extract the heat from the bottom so that the growth will start from the bottom to top. Whereas here, after melting, there is a seed crystal, mother crystal, small seed will be inserted into the melt. Then there is a equilibrium will get disturbed, and then this melt will start attaching with the seed. Then you have to maintain, you have to pull this seed, in a controlled way with the rotation. And the same time, crucible also will rotate opposite direction. So by rotation of by pulling speed and rotation speed, crucible rotation, so you can maintain the diameter. What is the size you want? Everything you can control. What is the length you want? All the and everything you can control through pulling speed and rotation, and also crucible rotation also. So automatically, after some time, the crucible level also will come down. Level slowly when the melt is converted into the solid crystal, the melt volume also will come down at one stage, very small amount of, then you have to take it out. Then earlier, maybe a few years before, once you complete this crystal, then you have to stop the complete furnace, you have to take it out, this crystal, and remove this crucible, put a new set of crucible, and again you have to load it. But now recently, what is happening, as I said, instead of using the crucible only one time, so you can still maintain some amount of volume here. Instead of taking out 100% of melt, you maintain certain 30% or 40% of the volume of the melt. Then take out the crystal out, then put the material again, then start melting, then put the another seed also again. So by using the same crucible, you can grow 4 or 5 crystals at a time. In that way, you can minimize the, you can increase the productivity, and less time you can produce more number of crystals. So that, productivity and crucible cost also will come down. So this is the way industry is also developing, how to improve the productivity and also reduce the overall cost of manufacturing and also improve the quality. Right. So as I said in my previous slide also, China in the wafer, unfortunately wafer, when you talk about ingot growth, 98% right now is dominated by China. The rest of the countries only 2% or 3% overall wafer manufacturing capacity. So even 98%, only few players they are dominating. And until November 2022, India has no wafer manufacturing capacity industrial scale. And only few countries like other than China, Vietnam, Malaysia, these countries they had they started few wafer ingot manufacturing. But once again, Chinese players only they set up the facility in Southeast Asia because of US government. They put a lot of restriction on Chinese imports. And that's the reason Chinese companies, they set up the facility in the Southeast Asian countries like Vietnam, Thailand, Malaysia, and started producing this ingot wafer and this one. Unfortunately, India, there was no manufacturing facility of ingot wafer until 2022. But in 2022 afterwards, one first player, Adani Group, they started investing India's first gigawatt scale wafer ingot and wafer manufacturing facility in Mundra, Gujarat. And they started to the 2 gigawatt of equivalent capacity. So almost 2023 or 23 around January, February, around that time, India's first industrial scale was grown in India first time. So before that, of course, so many players in the world, in India, so many institutes, laboratories, they started growing small size crystals. But 4-meter length and 300-meter dia industrial scale, where you can produce the current wafer size of 210, 182, whatever the size the industry is lying. So first time they've grown, 2022 end or 23. So that was India's first, large size industrial crystals. Fortunately, I was part of that, project. So it was a happy moment for everyone. This is by doing this, you can grow, this almost 4-meter length of crystals, this one, the crystal grow will be like this, almost 300-meter, mm diameter and 4-meter length. Shall I continue this one?
Yes, you
how
can
much time I
go
have?
on, still 20 minutes available, sir, if you like, sir. If you like, you can continue. Otherwise, you can talk about the question and answer.
Yeah, I think maybe I can continue tomorrow also. Maybe if someone wants to have some.
Yes, sir.
questions.
We will have some discussion. The talk is open for discussion. I would like to thank Dr. C.V. Kannan. He has an excellent talk for regarding the industrial silicon orientation and crystal growth techniques. I will thank to the Dr. C.V. Kannan. Now the talk is open for discussion. The faculty members and students may ask questions. Welcome to the questions.
Still,
Hello?
I have so many slides.
Yeah, yes, sir. Yes, sir.
Sir, this is
hello,
Dr.
Yeah,
Riyaz,
please.
sir.
Yeah, yes, Riaz, tell me.
Yes. So I have a small query, excellent talk, sir. I have a small query about the solar waste. How government is projecting to maintain the solar waste, because nowadays everybody is going to set up a solar cell, but after 5 years or 10 years later, so silicon solar cell will be the more waste material will be the most one of the problems. So how government is focusing about the solar waste?
Yes. I think this is one of the major concern, like electronic waste, not only solar waste.
Yes.
Overall electronic e-waste, that's the next big industry, like renewable energy. So we are talking about more renewable energy, more electronic industries. So the other way, how we are going to, reprocess after 25 years or 30 years of, life, end of life. Because unfortunately, in India, I think the growth, the solar panel installation started maybe a few years before. Maybe we will face this problem maybe after 10 years or 15 years only. But some of the Western countries who have installed these panels maybe 10 years before, from 10 to 15 years before, probably they may face this challenge very soon. So entire global, overall, internationally, people are also working on how to recycle this one. And there are a lot of recycling mechanism have already established, but it's not, I don't say it's 100% well established. Still a lot of challenges in terms of cost optimization, right? And but India also, a lot of research is happening in the university level, institute level. Government is also putting a lot of efforts, how to recycle these panels, right? And how to recover the material, whatever the material we are using, because in the solar cell we are using some copper metals and aluminum frames, and the glass and silver also we are using in the solar cell manufacturing. So people are trying to recover as much as possible, and also recycling mechanism also enforced by the government, every manufacturers. So they have to be part of PV recycling, certification. There is a organization body. So if you want to manufacture, you should be part of the PV recycle. So after that certain, end of the life of the product, so they will, if you are a member of the PV cycle, so the manufacturer probably they can, the PV recycling agency, they will take those panels and do the recycling. Right. So the lot of companies are being set up how to recycling all those things, but fortunately there is no major e-waste in terms of like there is no hazardous material being used in solar cell manufacturing except small lead is being used in this module manufacturing. Otherwise, all are recoverable, like aluminum frame. You can reuse it. You can recover it. And glass, of course, it's once again sand. It's not going to harm to the environment. But only thing is you cannot throw it just like that, right? It has to be properly, recycled it, and whatever the valuable material, you can recover it like a silver, aluminum, and copper also ribbons is there. So all this material you can recover as much as possible. Remaining you have to throw it. But unfortunately, this not there is no hazardous waste being used in the solar PV manufacturing, right?
Okay. Thank you, sir. Thank you so much.
In this concern,
Excellent talk.
sir, I am Dr.
Hello, sir.
Saravanan from Chennai. So in this concern, the waste of silicon from the used solar cells, they are foreign, as sir said, in abroad, they already started to recycle this silicon in the lithium-ion battery application, that they are mixing the silicon powder, they crush it and make it powder and used with graphite for the electrodes in the lithium-ion battery.
Yes. Actually,
Yes, yeah, you are right.
Actually,
Silicon is currently using for the anode material for the lithium-ion battery.
exactly,
Yes,
exactly. That is actually the slurry, the one, the pure wafer. When you convert the crystal into wafering process, lot of a slurry will be generated. That purity of silicon will be relatively better. So those slurries are being used for the battery electrode applications. Whereas what we are talking here, I think the silicon waste and the amount of silicon you recover from here, the purity of that silicon may not be that much good. And right now, as I said, the silicon cost has come down drastically from $30. Earlier it was $200, $400, maybe 10 years before. Right now it is up $6. So getting silicon, recovered silicon using for electrode and pure silicon during the cutting process slurry, that is more cost effective than the recovery. So that's the reason during the recovery process they focus more on the valuable material like a copper. The price
gold
is
also.
getting increase.
Gold also from the e-waste.
E-waste. Gold is
from
not
the
coming
gold.
from this one. Whereas in the PCB circuit, a lot of gold deposition is happening. So they're trying to recover the gold. That's one of the important valuable materials.
Yes, sir. Thank you, sir. Thank you.
Okay.
Any other questions
Hello?
from the faculty members and students?
Hello.
Yes, please.
Hello, sir.
Yes, please.
Sir, you discussed a different growth technique for single crystalline and multicrystalline and polycrystalline also. But my question is how the grain size affects the efficiency. For example, polycrystalline grain size is less than single crystalline silicon solar cell. But single crystalline monocrystalline silicon 20% efficiency, but the polycrystalline is 12% efficiency. Is there any relation between the grain size and the
Yes, of course. Because why monocrystalline? Single crystalline always, the performance parameter, a characterization of, the orientation, particularly single orientation, whereas the multicrystalline is multiple orientation. The crystal, the carrier transport or carrier, transport mechanism is different for different orientations. So when the sunlight falls on that, on the silicon wafer. So different orientation, they have a different electron hole pair will be generated, and the carrier will start moving against each other. But when you have a grain boundary, say a small crystal, it has to cross the other, go to the next crystal. At that time, if the grain boundaries are there, that grain boundaries are weak area where impurities may, the overall the contamination will be, all the impurities will be trapped in the grain boundaries. So when these carriers are going there is a chance of trapping of these carriers. It will not move forward. So grain boundaries are all weak areas, right? Potential trap areas. So whereas in the monocrystalline, you do not have the grain boundaries. So whatever the carriers are getting generated, it can easily pass through to the next stage. So that's why the lifetime, minority carrier lifetime in milliseconds, maybe 1 millisecond, 2 milliseconds. Whereas in the multicrystalline, it is in the microseconds. So whatever the carrier generated before it goes to the collection point, it dies. It dies because it is trapped in the impurities, which is lying into the grain boundaries. Also, the transport mechanism is different for different crystal orientations, right? Silicon, the different orientation, different crystal mechanism. So automatically, the efficiency will be poor. But right now, the slide I've shown 2012, but actually the crystalline silicon, multicrystalline, the efficiency becomes 18, 19%. Whereas the monocrystalline gone even 25, 26% with the different technology advancements that is happening only in the monocrystalline. Multicrystalline, because of the limitation in the efficiency, so they can, all the new technology, they are focusing more on the monocrystalline where there is a potential. You can increase the conversion efficiency further up because there is no grain boundaries. So grain boundaries are basically trap areas.
But the commercial now available in the market is around 20-21% only, sir.
No, that you can say, no, commercially there's a module efficiency. There are two different things. One is cell efficiency always higher. When you convert cell into panel, when you stitch all the cells into the panel, so the panel efficiency, because panel you have lot of empty spaces, right? And the panel efficiency will be generally thumb rule 2% lower than cell efficiency. When you take only cell efficiency, it will be 23-24% conversion efficiency. Same 24% conversion efficiency put into the module, the entire module efficiency will be 21 or 22%. So there's a 1.5 to 2% difference. But right now, cell efficiency is a 23% for mono-PERC technology based, and TopCon, which is a currently mainstream product, where you can see 25% also. And industry is also moving towards 26-28%, which is the target single silicon based solar cell efficiency. Maximum you can go to 28.7. They are coming very close to 27% right now.
Okay, sir. One more question, sir. Sir, in your industry, TP solar, how much efficiency right now you are getting?
Right now, we are running mono-PERC. We are getting 23%.
Okay, very good, sir. Thank you.
Any other question from audience? Sir, some audience are given the chat box question. Dr. D. Bharaniraj from Government Arts College, Ariyalur. Is there any particular orientation of the crystal wafer has maximum efficiency? Like that he is asking.
Sorry, say again.
Is there any particular orientation of crystal wafer has maximum efficiency?
That's what solar cell 100 orientation is the best, orientation normally used for solar cell applications. Right.
Okay, sir. Then another question from chat box, Sandhya Gupta. Sir, in multi-crystalline ink-out process, is there any possibility of presence of dislocation in the grown crystal during cooling process? If dislocation are present, then how can remove it?
See, that is the reason. Dislocation, you cannot avoid it because you are, forced cooling. Because you meant to molten it, then you are forcing, forced cooling mechanism. So unless until you do a very controlled way, there is chances of more, dislocations. But of course, you can also improve the dislocation by, there is a process called annealing process. After you grow the crystal, you heat treatment once again you heat it to some 70% of the growth temperature, like growth is 1300 400 degree, and if you heat it to 700 900 800 degree, there is a slight reorientation of the crystal grain, so that it will improve the performance to some extent but not fully. So you cannot compete with the monocrystalline equal to monocrystalline, but you can slightly improve the overall efficiency. Minority carrier lifetime, for example, 100 milliseconds, microseconds before after the growth. After the heat treatment process, you can further maybe 100 become 120, 130, something like that. There was slight improvement in the overall minority carrier through an thermal treatment process.
Okay, sir. Thank you.
Any other question from audience? I think chat box is only 2 questions are available. I think one more question. Does India have technology started from the growing crystal to making chip?
No, see, right now India, we have only solar manufacturer. As I said, Adani is the only company who set up 2000 megawatt equivalent capacity first time in India industrial scale. There are two PV application, photovoltaic applications, but the same CC method, you can use it for semiconductor application also, but the equipment design is completely different from PV application, but the method is same, similar kind of crucible, similar kind of all, but the equipment design is something different, where you can minimize the, because as I said, semiconductor needs very high pure quality of wafer, so the contamination from crucible also will be minimized. So whatever the crystal you grow through for semiconductor, it will be very high pure. And but that semiconductor application crystal growth, there is no facility as of now in India. And recently even Tata Group also announced a big wafer fab manufacturing in Gujarat, but there also probably they get the wafer from outside, and only the fab process, which our previous colleague, my previous presentation, you might have seen how to convert the silicon fab wafer into the fab device. So that's a different, they're getting the wafer and converting the wafer into the semiconductor devices. And there is no silicon wafer growth for the semiconductor application in India as of now. Only
Sir,
PV application, many companies are coming up right now.
Yes, sir. Yes, sir. Sir, 2 more questions from the audience. Miguel Kumar, he asking question: why India not producing? Is technology costly? Like that, he is asking question.
Because it's as I said, it's a volume game. When all the raw materials are available in China, and 90%, all the equipments, all the raw materials, crucible, everything available only in China, and we have to rely on China importing everything. Obviously, cost will go up, and also it's a volume game, because 900 gigawatt capacity, we are having only 2 gigawatt capacity. Right, so how do you compete with China? So that's why the government is putting a lot of efforts to increase the internal domestic manufacturing in wafer also, so that more player comes into India. So automatically the ecosystem also will be generated. Whatever the raw material for polysilicon and crucible, all those will be internally available. So then you can minimize the cost to some extent. You cannot compete with China. At least we can come closer to the China.
Yes, sir. Sir, one more last question. One audience asking question, Vasu Alam. At high temperature annealing of crystalline material will lead to peel off from the substrate, like they're asking questions.
Sorry, I don't get.
No, sir. See, asking at high temperature annealing in crystalline material, whether the silicon is able to peel or not, like they're asking questions.
No, silicon is how to peel off.
See, it's not two-dimensional materials. The water walls cap is, there is no water walls cap here.
Yes. It's a single piece. There is no chance
you
of
cannot use them like that. I hope any other questions from audience. I hope everybody is enjoyed this talk. It's very excellent talk. Dr. C.V. Kannan is my one of senior, most far senior in the year of 2002. He has completed PhD. I joined the Crystal Growth Center 2003. Then I met many times, sir,
Sure.
and we are trying to always collaborate. Always still continues is going on the speaking always. When sir is in Adani, we are always talking to the how to grow the silicon crystal growth. Now sir
Thank
is
you.
moved to the Tirunelveli, the Tata Power. Still we are doing the collaboration work. Is if anybody interested to welcome for the collaboration to Dr. C.V. Kannan, sir.
Thank you, Dr. Tangavel, and we will continue tomorrow also.
Yes, sir.
And from
Tomorrow
here-
also will continue. Any question, then you note down. Tomorrow also you can ask the questions.
Okay. Thank you
Yes,
so
sir.
much.
Thank you very much, sir.
Thank you.